Thank you.
Okay. So, welcome to everybody to today's webinar about Introduction to Survey Sampling. My name is Heli Lehtimäki. I work here in Eurostat, and I am hosting, together with our WebEx colleagues, this webinar today. Now, for those of you who have been with us before, you would notice that the virtual meeting looks slightly different than in the past. It is because the Commission changed the service provider some time ago, and today is our first experience with a new web conference tool called WebEx. The main principle is like before. Participants are muted, but you can interact in the chat room. What is different today is the audio runs with the phone only, so I hope that everyone has used the toll-free numbers from the link you found in the invitation. Now, this is where we are struggling a little bit, but let's see. Otherwise, the cost of the international phone call would be on your phone bill. We would not like that. For anyone who would have missed our live session today, and for any other reason, the recording and presentation will be published online later. I would now pass on the floor shortly to David, who is our WebEx operator today, and then come back still introducing our main speaker later on. So David, please explain in a few words what the participants should know about WebEx and how to operate it.
Thank you. So, ladies and gentlemen, the main way to interact on this call is through the chat function. It's shown as a little speech bubble on your PC. So if you can locate that, you click into the chat bubble. You'll then be presented with a box where you can type your chat message, and then there's a drop-down box above that, and you can choose who to send your chat to. If you send it to all participants, everybody who is logged onto the WebEx can see your chat message. You can pick a private person off that list and send a chat message privately. If you find your screen's on full screen mode, you should be able to see a floating panel above that, and then you can locate the chat box from there as well.
Okay, David, that was it?
Yes, I think that will help them with the chat, which is the main interaction on the call, yeah.
Okay. In the meantime, I have helped the participant to the UK toll-free number on the chat, indeed. And, well, we'll get in terms with the WebEx as we go, but now to the session itself. It will be delivered by Ralf Münnich, who you see on the screen, from Trier University in Germany, which is not all that far from my office here in Luxembourg. Ralf is a member of the EMOS board, and Trier runs, in fact, 2 EMOS-labeled master programs, one for science in economics and the other in survey statistics. And as it happens, Ralf is a full professor in both subjects, and I think that you are in very good hands for today's talk. And Ralf, the floor is yours.
Thank you very much, Haley, for the introduction, and welcome to everybody to today's lecture, Introduction to Survey Sampling. I'm really happy to see so many people already joining this lecture, and I hope you will enjoy the next, 85 minutes. We will have 2 short breaks. I will follow what Markus Zwick did last week with some short questions that you can somehow recover a little bit, and that we come up with the next topics. So, when we talk about sampling, of course, we have to think about why do we need sampling. Certainly from basic statistics, we know that there is the classical EARN scheme, and the EARN scheme is so well elaborated that one could think that everything is fine. Indeed, in practice, we know that this is not the entire story, and today I will try to make it a little bit around why we need sophisticated sampling schemes. After the basic introduction, we will tackle a little bit single and two-stage sampling schemes that I think is one of the most important parts in survey practice. Most of the household surveys are somehow multi-stage sampling designs. Multi-stage means just that there's a little bit more than 2 stages, but sometimes you can put them together. And finally, today, we will tackle also regression estimation. auxiliary information is always a big issue in sampling theory, and but we can use it on sampling and on estimation itself. So that will be a little bit what we try to tackle today. Give a little bit more information in the overview you got from Heli Lehtomäki for this lecture today. So certainly the audience is has a huge variety. That's sometimes it's a little bit boring from those for practice, and sometimes a little bit boring from those from universities. I try to make somehow a compromise, but certainly we try to tackle also the basics. So if we talk about statistics, the major aim of statistics, especially for official statistics, is gathering a provision of data for administrative, political, sociological, economic, and other research purposes. This information is obtained in universes or samples of units, persons, households, establishments, and so on. The data are gained in total or via pre-specified principle, partially as samples. That's the big issue. You see here already randomly quota samples. There are a lot of different issues which we have to tackle, and the following shall be considered. Certainly primary and secondary statistics. Sometimes you draw samples for other reasons where you use the data later on. Registered data is a nice example of that. Problems of adequacy is a big issue, of course. Errors have to be considered, and well, the things which universities don't like so much but which is important is data protection or anonymization of data, and certainly this also has a big aspect which we have to consider. So if we talk about surveys, a survey in general is the methodology for gathering information via samples on persons, households, and other units. And in the survey, we have very different items to consider, like planning and development, pre-test, survey design, implementation, data gathering, editing, processing, and analysis. There are some nice overviews. You see the 2 links below, and later on, if you have the PDF slides, you just can click on that. Today, certainly, we cannot tackle everything. We already had nice lectures for the planning and pre-test. What we do here today, of course, is more tackling the survey design. And, of course, the survey design has impact on the analysis because we want to draw, of course, different values, totals, means, proportions, tables. You know all the famous tables in official statistics, and that's our main purpose. Certainly, there are quite a few of applications all over the important things. Certainly, we are more focused on economic statistics, empirical economic research, sociology, demography, market and opinion research, quality control. You see many, many different areas, and certainly official statistics covers most of them, but there are also other areas which might have different ideas of sampling. If you are more towards environmental statistics, then of course different schemes are in focus than if we talk about household surveys or business surveys. We tackle more the last part. In the next lecture, end of June, we might expand it a little bit and think about other things. So when talking about data gathering in surveys, we have different kinds of data which we have to consider: cross-sectional, longitudinal data, then time series and panel data. And to be honest, today we focus more or less only on cross-sectional data. Certainly, rotational panels are used as well, but the main focus currently in the sampling we do is on cross-sectional purposes, so that's what we consider here. There are theories, of course, like for rotational sampling schemes and others, but we cannot do everything. That's an advanced lecture. So in data acquisition, we have a lot of different things, but I think we will tackle directly the sampling schemes. But you see, we also have snowball sampling and quota sampling, and I try somehow to consider that a little bit later. The difficulties, what we draw now from that is these are non-random samples, and we are interested certainly also in inference on statistics, that we can somehow measure the impact or the outcome. And if you have non-probability samples, this, of course, is much, much more difficult. And there are not so classical schemes as we have in sampling theory. That's why we somehow drop them. Okay, then to give some examples, Some very important European examples here we have is the statistics on income and living conditions. That's really a lovely survey. Or the poverty measurement comes from that, very important. And my students, of course, know this quite well, like from the first lecture in the first semester of the bachelor, I start with this. Then, of course, the European Social Survey. We will somehow indirectly tackle that in the second lecture because this gives a very interesting idea of comparability between different countries. There's certainly a huge impact on sampling designs and finally also on variance estimation. What else do we have? Then we have the microsensors. And the reason why I make that is it's not that it is a German survey, and I know it quite well. It's more or less that some of my examples are coming from that, but it's a very nice classical household survey. So to give some ideas on that, it's a 1% sample coming from 1957. There was a big reform in 1990, some changes, and what we have, and you see that since 2005, we also have short-term sampling, and the microsense is, in the meanwhile, is a rotational panel. So every year, 1 quarter is changed. Even if we tackle it as a cross-sectional survey in this lecture, of course, if you're interested in changes, then you have to consider this rotation quarter, which is not overlapping. To give some more information, we have regional classes. So we have somehow a stratification towards regions. A little bit unlucky that I already talk about strata, even if you haven't been talking about stratified random sampling, but to give some ideas, the regional classification, the classification with respect to house size classes, so you have small buildings, mid-sized buildings, large buildings, institutions, and new buildings. And what you see is somehow the size of them. And then we have a selection domain, which means that for the small buildings, you put some of them together. And for the large buildings, you take equal one. And if you have institutions or new buildings, you certainly have to think about the difficulties in institutions and new buildings is nothing else than the earlier ones. So very important to remember, especially if you talk about the variance estimation in the next lecture, is that the sizes we are drawing finally the small strata, small groups in that, is that the difference in the sizes are really extreme. So altogether we have something like strata, different kinds of strata, and finally clusters. And the clusters is the important thing that, like for the mid-sized buildings, one mid-sized building is one little cluster at the end. And from the small buildings, you put some of the buildings together. The large buildings, you take like something like floors. And now you see how the different clusters at the end are put together. Finally, these clusters are put in one row. And from 100, you draw one. That's where we have the 1% sample finally. So approximately 1% of the individuals and households are drawn, more or less exactly in terms of the so-called Auswahlbezirke, so the final clusters in this case here. If you put then 4 of these 100 groups together, each year you change one of the blocks and rearrange that. That's how you get the rotation quarter inside. So that's important to understand roughly what we do later, that we have clusters of size approximately 20 persons, but that can have some variety, of course. And very important for us, EU Silk and ICT is finally drawn from the microsensors. Once the people are dropped in the 4th year, after 4 years, all 4 quarters are somehow changed. These people are asked if they would like to participate further, and from this access panel, Silk in Germany is drawn. Fortunately, we do not need that yet, and that's a little bit sophisticated. And the good news is that the microsensors in the future will be rearranged, that it is a core sample, and that you have this integrated household service system, that all the other samples are directly sampled somehow from the microsensors. That gives some very new ideas, and that's important if you talk about regression estimation to get some gain in efficiency. So what else is of interest? Of course, we are always interested in data quality. You know, all of you know the European Statistics Code of Practice, and it's only part of it. So, of course, relevance of the statistical concepts is very important. Accuracy and reliability. And if you talk about accuracy, we are already in the field what we are directly interested in this lecture. This especially is sampling errors. So standard errors, confidence interval coverage, and all these things. We will go a little bit more in detail soon. But also, of course, non-sampling errors. I try shortly to tackle that a little bit in the variance estimation part in the next lecture, because certainly this can have huge impact. You have to correct for non-response, but in the basic part today, I will somehow assume that we have no non-response. I know it's a little bit kind of wonder world. In practice, you have non-response, but that comes a little bit later. Timeliness, punctuality, of course, is important. Coherence and comparability, accessibility, and clarity. All these concepts certainly have a huge impact on what you can choose as designs and how you can arrange that. But as I said, our main focus today will somehow be here on the sampling errors. But before we tackle that more, we have to understand what more or less sampling means. Errors certainly occur in many different kinds. Non-response is one. Frame errors, interviewer errors, processing errors, coding errors. Non-response, and finally the sampling errors. So there are a lot of errors, and but the core thing certainly will be this one. To be honest, most of the errors can be somehow compensated, but that will be rearranged like with calibration techniques or other techniques or imputation. I will tackle parts of it later. So to understand how I tackle the lecture, my students who have somehow passed the Master in Service Statistics always know the main principles. I'm chasing them through every lecture. I see some smiling here, which you don't see here. Some know that already. So the main principles, never, ever forget them. Certainly, if you talk about sampling and you want to do something else than drawing just from an urn, you have to think about different things. Well, to give an example, like if you want to see the infection rate of a cornfield, it would be not very wise to take an urn scheme. Why? Well, either you cut the entire cornfield, put it in an urn, draw some of that, then you can somehow estimate the infection rate, but that finally at the harvest there is nothing which is remaining, which is not really sensible. The alternative would be to take each single corn, put a number on it, and sample, and later on, once you have been sampling, you have to find the straws. And that also is over-sophisticated, so you have to do something else. And the question, of course, is how do you construct something else? Any idea? Well, since it's not really an interactive lecture, I have to do it myself, but be sure soon there will be the first set of questions. Certainly one thing is that you really can do it in a practical way. So enumerating all the corn would be a disaster. It takes by far too long. So what would be possible is like taking a square meter, throwing it in the cornfield, and once you have done that, looking for that square meter, take the corn, take the infection rate, maybe not only 1 square meter, that's too less, but at least then you get some proxies. We will soon call that cluster sampling because you take the entire 1 square meter. What you also could do is taking the cornfield and putting somehow a grid over it and then taking grid cells. So that's the main purpose here for practicability. You must be able to draw samples. That's very important, and even if you have a very interesting, sophisticated, very efficient design, it may be that you will not be able to do that in practice. Then we have so many guests. I have seen many statistical offices. They always have the big issue of costs. They don't exceed the costs too much. Of course, as a mathematical statistician, I say, well, we need efficient samples. The accuracy must be very good, and not everything can be just the most sophisticated estimator. So, but this certainly means raising the costs, and they have to be put somehow in a range which you can sell your politicians who have to be responsible for the budget. And finally, if we talk about sampling or the analysis later on, we want to make sure that you get very good results, and that means the accuracy. And accuracy for us always means that we have kind of variance component inside. So the variance of the estimator, whatever estimator we take, has to be controlled. That should not be too large, and of course, all three concepts have different directions. Not everything which is practicable means it is very good or it has low costs. Everything which gives accurate estimates might be impracticable or, again, large costs. You have to compensate that somehow. And finally, what in the meanwhile I added means the robustness of the results. It may happen that you optimize your design in a very, very, very sophisticated way. And finally, you find out that the information you used to optimize the design was not the best information you could get. And if then it happens that the entire design breaks together and gives you bad results, that would be a disaster. So somehow you should control, during the optimization process, also the robustness of the methodology and finally of the results which you want to do. So to add some other basic principles and statistics, in addition to the analysis from survey data, we need to investigate the quality of the results. The aim is to generalize results from the sample to the universe. That's the classical idea of inferential statistics. Working with samples, but somehow expanding it to the universe. And that means we have a sampling function or an estimator. And certainly if we have an estimator, we are very much interested in the properties of the estimator. So that's very, very important. And nowadays it gets even more important. If you look about the buzzwords like small area estimation, some of you have heard that. The problem in small area estimation, it's a model-based world, and probably some of the properties sound different than in a classical design-based context. The design-based context is that what we will teach today. And if you talk about general properties and estimators, we first think about unbiasedness, efficiency, and probably if you talk about confidence intervals or something like that, we need normality. But normality means we are talking about limiting theory, and that means large sample properties. Very, very unfortunately, we are talking about finite samples, and the question is, of course, if we have finite samples, let's take a sample size of 10,000 inhabitants, is that really large? Any idea? It sounds large, but we will soon come to an example where you see that it might not be really very large if you talk about thousands of inhabitants, and that's why we are essentially also interested in small sample properties. And the question is, when is small and when is large is not so easy to answer. Even nowadays, if you talk about small area statistics, sometimes you find out that, well, already the sample is not so small, or vice versa. Or everybody like Markus Zwick 2 weeks ago was talking about big data. You seem to have a huge amount of data. And the question is, what can you say about that? And probably even in these cases, sometimes some strange properties occur. And certainly for us, we need the right measures to understand what we do. And the question is, how can we do that? And later on, we will see also that possibly if you have one sample, you cannot observe all the properties. You have some ideas with the estimators. You have some ideas maybe about efficiency and about normality, but maybe you're somehow spoiled about the example. And to show you what it means, I have here one example, a classical table of unemployed people. That's a classical table, the split of unemployed between in gender and age classes. To be honest, that's from one of our simulations. That was one of my first big projects, the duck size project. And you see here the two numbers. Very fortunately, at that time, we had a universe, certainly not the Microsensors universe. And here you see we used the Microsensors sampling scheme, but we were synthetically expanding that we have the real somehow real or realistic settings in the federal state Saarland. The federal state Saarland consists of approximately 1 million people. A 1% sample means 10,000 inhabitants, approximately. So that's why I used is 10,000 big or small as sample size. And if you see the table here, then if we repeat it, drawing estimates from the microsamples and take the average over 10,000 simulation results, we probably get, we should get, here they are, somehow the average of the estimates. And we see very little differences in most of the cases, like here, it's exact. Here there is a tiny difference. And the question for us, of course, is the quality of the cell estimates identical? And I will tackle somehow these two values, surprisingly. So one, more or less, small value, of course, the elderly women, unemployed women is somehow a rare event. And then a classical group, 25 to 44, where we have more observations. And certainly my question to you is the quality the same of that? The simplest answer would be, well, we draw one sample, the microsensors. Why should we have different quality? It's one sample outcome, and this one sample outcome is somehow thrown over a table. Even if you don't see here single estimates could be one outcome of this study. We try to tackle that directly. That's somehow from a simulation result we have. You see many different estimators. Don't worry about the names. Taking a classical mean estimators or proportion estimator, what you hardly can see here is that we have a blue and a red line. One is the truth and the other one is the average from the simulation. What you also see is that we somehow have 4 different box plots, and this is with respect to the non-response rates. So you see, even if we don't tackle non-response here, we use a classical raking estimator, which is a calibration estimator to compensate for non-response. You see that for all these estimators, the average of the outcomes is exactly the same as the true value. And what we need to go into detail in the next lecture, even the variance estimators, we see the more non-response you have, the more loss of efficiency you have with the estimator. But we see that even in the case of a lot of non-response, we were somehow able to compensate that even as in the variance estimation case. The lower bottom figure shows somehow the confidence interval coverage rates in our case. And we see here that the nominal coverage rates, either for 90% or 95% confidence intervals in our simulation study, went fine. That's the wonder world which we like. So we see somehow implicitly that our inference works well, at least for this case. But please do not forget, if you have only one sample, you cannot draw this figure because that's a repeated measurement from a simulation study. And that's already one answer to my question 5 minutes ago. One set of measures is dedicated to the outcome of one sample result. And if you're interested about does the methodology work, you might additionally think about simulation studies. Don't forget that. We will somehow tackle that later and talk a little bit about simulation studies. So in this nice case with a 7,000 whatever people, I apologize that I didn't have the graph with English names. That means unemployed and density, or variance. In the German word, it's written with a C. You see there's quite nice normality, and as I said, the blue and the red line, they're almost lying on each other. So this is the nice case. But what happens with the other age group of unemployed women? If we look at about that, we see, oh, we have very skewed distribution. The box plots look very suspicious, but even so, the blue and the red lines are again on top of each other. So on average, the methodology works. And that means the law of large numbers for the point and the variance estimator works fine, but there's no normality, and that's the big issue. And if you look now at the coverage rates, wow, they were somehow collapsing. By the way, typical case, if you talk about small area estimates in a design-based world, but here we have it already in design-based world, and that's not really fine. So very problematic, and the question is what happened here? If you look about the detail, now you see somehow the sampling distribution. The point estimator is here on the left-hand side, and you see somehow you have a bumping distribution. Even if on average you're correct, if you don't try to draw inferences, you see a big proportion either here or here is somehow collapsing. So you have many estimates, many samples where you did not observe any of the unemployed women, or you have some where it's somehow exploding. Even here is some mass, so extreme overestimation by factor 5. The question, of course, why is that? And now we have to come back to the microsensors. It happened that some of the clusters of the elderly unemployed women were living together. And now you have the effect that they're somehow clustered in one of these clusters at the end. So what you have here is somehow, I could say, outlyingness by design, because they're put together and then this can happen. And if this happens, then of course the so-called originally large samples can be extremely small. So here we would say, even if we have a sample size of 10,000 inhabitants, due to the clustering we have problems which come from small sample properties. So really amazing. I mean, further amazing is that the variance estimator looks better than the point estimator, but that's somehow, well, nice besides result. Nevertheless, you saw that the coverage rates somehow failed entirely. So very important for us, of course, is to understand that, well, outliers always are problematic, and they cannot happen not only with outcomes of single observations, but also if somehow several observations are clustered and are somehow extreme, then we might have some problems. And this leads directly to the first set of questions, and I will use it for a 3-minute break that you can think about that. Even if the chat room for me is of size, I think the size of the letters is a 5-point font, but I will try to read it. So how would you evaluate survey estimates? And what has to be considered using simulations for an evaluation? In the last example, normality was not achieved. Is there any opportunity to avoid the lag in normality? And finally, the theory of simple random sampling is well elaborated. Why should we then consider other sampling schemes? So I leave you the first 3 minutes to think about that, and then I will answer that.
This is Heli speaking. I would suggest that you start. I understand that Ralf's meaning is to put answers on the chat room, right?
That would be great, yes.
That would be great. So I hope that everybody has found the chat, that you have to click on the icon to see the chat room, and you will be able to start putting your answers on the chat for everybody to see, and then we can take the discussion from there.
And now is the question, does the chat room work, or did everybody find it, or are you too shy? As shy as my students who don't dare to say anything.
Well, I suspect that there is probably an element of it all, because I think that if those who are not really familiar with the tool, it's not evident to find the chat box if you don't know where it is. If you don't hover your mouse on top of the top part of your screen, and you will see sort of floating panel there where you would see participants, chat, and annotate tools. And the chat icon should be blue. And then the chat box appears on your screen. Or you are in a view which is a little bit more scattered, where you see the slides on your left and chat room on the right-hand corner, you would have a chat icon on the top corner there that should also be blue. And I think, Ralf, that we have overall a number of people who are with us here on the WebEx space following the virtual meeting room, but who cannot hear us. So there is also that, but maybe they didn't have a toll-free number from their countries or something, but at any rate, we will have the recording later to share with them, and we take our lessons learned ourselves from this exercise to the next one. But we would have good 15 or 16, 18 people who should hear us and should be able to answer on the chat room if they have found the chat. Or, Ralf, you post questions that, you know, requires a lot of reflection.
I thought the idea from Marcus was so nice to ask some questions, and my students are very much used to it because I permanently do that in a very rigorous way indeed. I can hear yes.
Yes.
They're happy that I'm somehow blocked today, that I'm not so energetic pushing all answers.
David,
should I continue? It seems nobody...
Ralf, yes. See what David, our operator, is suggesting, to invite them ask audio questions if they wish. Should we try this? Now that we are... So that would mean that those people who are on the phone audio connection would not be muted, but could actually pose their question talking. Should we try this?
If you like. I hope that I are able...
Let's see what we get in. David, please go ahead.
Okay, so ladies and gentlemen, to ask an audio question, please key star then 1 on your telephone keypad, record your name, then press the pound key or the hash key. That puts you in the queue then to ask your question. Thank you.
David, I'm not sure that everybody in the audience knows what hash key and pound key is because they are not all British mother tongue.
Okay, so I'll open the lines.
Haley, may I interrupt? I think I fear a little bit that this might take too long. The alternative would be everybody has the questions. There are 3 sets of questions, and that they write an email to me. I hope that I can cover all these possibly many emails. I'm optimistic. And that I start with some of the answers next time.
Okay. Okay. I think that you are in charge, so I think we proceed this session.
Since nobody has used the chat room, the answers are so easy for me.
Okay. So
unless David said that already some came in.
Okay, very good. Then just go on.
Okay. I suggest that everybody thinks a little bit about that, and next time we will cover some of the questions. I think the first question, of course, is a matter of taste and a matter of tradition, and one really has to think about that. And I know that NSIs work differently, but it might be interesting to see the differences. The question 2 is specialty from Trier. We work a lot with simulations. And sometimes simulations, for me at least, seem to be more nice examples, but one has to be careful what the outcome can really be. And certainly the last example, that will be tackled anyhow later on. Well, in a design-based context, we will never be able to get rid of this effect of the last example unless we raise the sample size dramatically. I mean dramatically, but in a model context, we certainly can cope with that. But in a model-based, not in a model-assisted context. We will see that partially, maybe at the end if I have some time. And certainly, simple random sampling, we said that already. The 3 aspects of sampling, they're so important, and simple random sampling does not answer many of the things we could do more efficient or more practical or with lower costs. And that's why certainly we need other designs. Before we can somehow talk about the different things, we need some notations. I try to use a classical design, and that means we make the difference between universe and sample. There are a lot of different things, and very unfortunately, the classical sampling literature uses capital letters for universe values and small letters for the sample. Unfortunately, people in statistics use capital letters for random variables. In our case, we in general see what is a random variable and what is something from the universe. What we are interested in, as I said earlier, is estimating totals, proportions, or means. Many of my examples are means to make it slightly easier, and we use Greek letters, tau for total, eta for proportion, mean is mu, or ratios here, and the estimates use a hat, just to make the distinction. I will somehow jump a little bit over the classical things. Certainly we have the population parameters, which is, since we're finite population sampling, which is nothing else summing up over the entire universe, the values y of the variable of interest, and we do it certainly similar with means, proportions, and with the variance. And we have the sample values, of course, here in the classical sample of a size n, then we somehow add them over the sample. Be careful. Currently, we have only simple random sampling. Later on, some of these will change a little bit to make it more clearly. But if we talk about sample design, unfortunately, we have to start a little bit about what is the basic settings for sampling. Why is it different when we talk about sampling inference rather than classical inference from a random variable? As I said, we talk about finite population sampling. Finite means that we have a sample which is somehow, well, a collection, I don't dare to say subset, we will see that soon, of elements from the universe, and the universe has cap n elements. So that's our finite population. Now we have, not only in simple random sampling in general it is, that we have to make the difference without replacement sampling and with replacement sampling. And without replacement sampling is much easier in the terminology, but certainly gives some additional problems. The sample here in this case is just a subset in the mathematical sense of the universe, so the writing is pretty straightforward. Sampling with replacement is slightly different. The sample consists of an index set with all the indices from the universe in which the elements may appear several times. So the number of occurrences in the sample. So if you then want to talk about a sample of size n, if you somehow add all numbers from the index set, that should sum up to small n, the sample size certainly. But it may happen that some elements are drawn 3, 4, 5 times. Practicability means it can happen, but in general, we would like to avoid that. It doesn't make sense to interview the same household again and again, but theoretically, certainly it can happen, and we have to consider that. So the first definition is, let U be a finite population with cap n elements. A sample S is generated with the help of a sample selection scheme that selects elements from the universe. The set of all possible samples with respect to the sample selection scheme is denoted by this S with a double line. The probability of drawing a pre-specified sample J, so they are somehow all enumerated, is the probability of Sj. Well, now what we could do is write down every possible sample, look for the probabilities of the sample, and that looks to be very, very straightforward. Well, we know already if we have, let's say, in Germany, the microsensors, the universe is of size approximately 82 million. 1% from the microsensors is then roughly 800,000 as sample size, and imagine the enumeration of all samples. Have fun, I can say. So we must do it more practically at the end, and that's very important. Before we think about some details, we make an easy example. So if you want to follow that and get some more explanation, it's from Sharon Law's textbook from '99. and we take a universe with 4 elements. So that's the case where we can write down everything. Sampling with replacement with a sample size of n equals 2, and then we have these kind of samples here, S1 until S6. All samples, and now we have 3 different possibilities. The first one is all samples are drawn with equal probability. That's the very straightforward case, so we have 6 different samples. Every sample has the probability 1 over 6. So the second one means that some of the probabilities are 0 for the samples 3, 4, and 5, and then you see different probabilities here. Strange to have very different probabilities for different kinds of samples, but that can happen in practice. Where we see that later, why it might make sense to think about different probabilities. And finally, we have just a small variation from 2 to 3 is the probabilities for the samples are again, they seem to be the same as before, but now we have 3 other samples with probability 0. So what is the big difficulty if you look at that? Well, it needs a little bit time to see that, but if you look at the samples 3, 5, and 6, we have these 3. And unfortunately, all samples are dropped, which include the element 4. So element 4 cannot be sampled anymore. That means for us immediately, this sampling scheme is not so good. We are recorded. I should not use the classical words I used, but it means for us in statistical terms, it's a biased estimator. No matter what the outcome of sample of the element number 4 is, we cannot achieve that, and all averages remain constant there. So that's a big issue, and we have major problems. But the question, of course, is, well, we have here the samples, and we are interested somehow in so-called inclusion probabilities. What would be the probability to get element number 1 in the sample? Well, we see element number 1 is in these 3 samples. And these 3 samples, in the first case, to make it easier, 3 out of 6 over the same probability is 3 over 6 is 50%. So in the first scheme, the element 1 could be sampled with probability 50%. We'll later see that this is a very essential property, and if you talk about generalized designs in 4 weeks approximately, so no, it's more, it's the end of June, then we will see how the Hurwitz-Thompson estimators directly uses these so-called inclusion probabilities. For now, it's slightly easier. We think about the first order inclusion probabilities. How I did that is I was interested in the element I and was looking in which of the samples did I find the element I. I certainly consider all samples in the entire set, and this is the classical indicator function. So I count the probabilities. If I find element I in sample J, and I don't count it, so the indicator function would be 0 if I cannot find that. Shortly go back, oops, sorry. Here it was 1 over 6, the probability for the first sample, 1 over 6 for the second, and 1 over 6 for the third sample. So the first order inclusion probability, well, they are all the same, is 3 over 6, 50%. If you take the second one, then of course you must look here for 1 over 3, 1 over 6, and 1 over 2 to get the entire probability. And this is, count that, and then you get the inclusion probability. Well, 3, 4, and 5 are dropped out. No, the 1 is not in there, so you have 100% already. Strange kind of way, but the question, of course, could be, does it make sense to get one element with probability 1 into a sample? Any idea? We'll later see the concentration principle. If you have very influential units, like in business surveys, it might make sense to get them in the sample. Certainly, these institutions would not be happy if they know they're sampled with 100% probabilities and others are not sampled. But just from accuracy reasons, it might make sense. We'll see that in easier examples. But for us, with the first order inclusion probability, what we do here is to make the difference between the classical inference and the inference coming from sample designs. And what we see here is we talk about the so-called design expectation, or we get the design-based expected value, because now the random variable is which sample do we draw. It's not the classical random variable, like you have a normal deviate or something like that. So we draw the different kinds of samples, and then we look for an estimator, a general estimator that can be a mean or whatever, depending on the outcome weighted with a probability to get this sample. The design expectation is nothing else than the expectation of the outcomes over all samples. So it's similar somehow to the classical random variable concept, but certainly here it reads different because we are in a finite context. But that's very important to understand that. In a very similar way, you can define the design variance, like with a variance formula, or the mean squared error, or whatever. And amazingly, this holds for all designs. It's independent from the design. As you saw before, we were defining 3 easy designs. We knew that one design doesn't make sense because it automatically yields biased estimates, but we can generalize that. And now, if we look at these, we make some examples, like simple random sampling without replacement. Sometimes the people write SRS-WR for with replacement to indicate that. I find it redundant, so in general, I try to avoid it unless I really want to make sure you see the difference. Another one would be Bernoulli sampling. Each element of the universe will be selected with probability theta. So you go through the entire universe. For each element, you draw a coin, and with a certain probability, you select it or you don't select it. Or systematic sampling is another one. You draw one element, and then consequently you follow like in equal steps to get other elements. So the question, of course, what is the big differences and what is the impact of that? In the first 2 cases, you predefine the sample size. Like simple random samplings, in general, you have a fixed sample size, and that's predefined. In Bernoulli sampling, you have a selection probability for each element, and then the sample size is a random variable. So the expected sample size then, of course, reads theta times cap n, the number of elements in the universe. Certainly, if you want to compare them in general, you said somehow that this should be somehow equal small n, but it not necessarily has to be. So the question, of course, here would be, what is the big difference? Well, the expected sample size means that you can have samples with a much higher sample size, but also with a much lower sample size. So you would get an additional impact on variability of the results just by the sample size, not only by the randomness of the selection process. That, of course, has a further impact if we later talk about variance estimation. So let's first come back now to the easy sampling schemes. Later on, we will come back to that and talk about sophisticated and generalized schemes, and certainly how we bring the classical scheme in this context. So simple random sampling, a random process in which successively small n elements are selected from a finite universe with cap n elements is called random sample selection. The result from random sample selection is called random sample. And now what is simple, drawing samples from an urn with or without replacement, is called simple random sampling. So the classical urn scheme is what we first consider. What do we have to tackle here? Well, in the case of with replacement sampling, we have cap n to the small n different samples. And very important here is we have one advantage, and the advantage is that all draws are stochastically independent, because once you have drawn some elements, with the next draw, you have the same elements which you can draw. So there is no dependency from draw to draw. This certainly changes if you're talking about without replacement sampling. Even if without replacement sampling is that what we would like to do because we don't want to interview people again and again, this seems to be more difficult because here we have to make sure that in the second draw you cannot draw the first one again. In the third draw you have to consider the first two draws. And then, of course, this seems to be very difficult. But if you come back to the first order inclusion probability concept, then of course we see something very interesting, like in the simple random sampling without replacement case, the inclusion probability is small n over cap n. Well, why is that? Well, you're interested in one special element. You take all samples where you have one element, the number I defined, and the rest can be whatever. So you take the variation of them over all variations. If you divide them by each other, you get cap n, small n over cap n. So if you then come to simple random sampling with replacement, you see the formula is much more difficult. If you tackle that, well, at least in this case, and you do it by the opposite probability, which means this one is here, means 1 minus 1 over n. Don't draw the element I, and you draw it n times. And this means you take the opposite probability of never drawing I. That means you automatically get at least once I in the sample. So the inclusion probability here seems to be slightly more difficult. The good news is if the sample fraction is very small, you have very little differences. But if you get higher sample fractions, then of course you might have big difficulties. That was at least to show you that you can put one in each other. So then of course simple random sampling can put in the classical theory. We know, of course, that simple random sampling is unbiased, also in our design-based context. The variance can be written very easily. I don't repeat that because that is somehow context of classical introduction to statistics. And what we are interested, of course, is somehow to know that we have normality, and this works with the classical estimators. Again, we have to make the small difference. Is the universe normal? In practice, I would say never, but in theory it can be. If it is not normal, the normality theory, the central limiting theory, certainly still works under its own conditions. And to summarize that, we have an unbiased estimator. If we take the classical sampling mean, it's consistent. It's, by the way, a best linear unbiased estimator. It's a linear estimator, of course, and you can also use maximum likelihood theory. Only in the case of simple random sampling without replacement, you don't see the difference in the mean estimator, but you see the difference in the variance estimator. You have the finite population correction. And this comes because you have a negative covariance between the different draws. And why is that? Well, if you draw a relatively high value, then certainly this high value cannot be drawn again. So it's likely that you get lower values. That's why you have somehow a negative correlation. And of course, that's of advantage because then we would expect to have a lower variance going to the model without replacement. Where do we use it? Sometimes in practice, we are certainly interested in the confidence intervals. We certainly have the classical ones. This is nothing else than the alpha half quantile of the normal distribution, and this means somehow we take the point estimate, we take the variance, the square root of the variance of the estimator, and that's how we construct the confidence interval. In the case of normal distributions in the universe, you can substitute the normal distribution by the t-distribution, but I don't want to expand that too much. Very interestingly, this follows certainly a very classical concept. For all estimators, and not only for the mean, which we tackle here, and amazingly, that's why you should memorize that, this works for generalized sampling scheme. Whenever you have a mean estimate, the confidence interval is constructed in the same way. The only thing which you have to consider is here the variance of the estimator, and since you in practice don't have the variance of the estimator because this relies on values from the universe, you take again its estimate. The only tricky thing is, given often the normality assumptions hold. And we saw already an example with our unemployed women. With a higher size, it was fine, and the confidence intervals constructed in this way, and we used the raking estimators. They were absolutely fine. And in the other case, with our unemployed women in the elderly age class, we had severe problems. So the question is, when does normality hold is not so easy to answer and certainly has major impact on them. Now, as I said, beware of skewed variables and outliers not only in the sense of the values, but later on also in design. So that's something which is very important. Where do we need that in practice? In general, if you're in survey practice, you try to construct a necessary sample size. A necessary sample size means somehow for us that certainly we need somehow a margin of error, something like that. And one idea of constructing that is taking either the length of the confidence interval or half length of the confidence interval, which we did here. So and then the error should not exceed a certain threshold. And having that, we are somehow extracting the sample size. And if we then extract the sample size and reformulate that, we get the minimal sample size, knowing that half length of the confidence interval should not exceed our error margin here, and that's where we get the minimum sample size. So what's the big issue here? Well, one thing was already named, the normality assumption. We saw examples where we have to be careful, but even more difficult is that we have somehow here the variance or a variance estimate for our estimator. We didn't sample so far. How and where do we get the values? Well, one possibility would be, do we have information from a highly correlated variable? Or do we have an old survey which is somehow related and we know the values did not change too much? So there might be some information, but indeed this is the critical thing here, which in general in practice gives problems. But certainly we want to make sure to have kind of minimum quality for our survey, and that's why we try to get information on good proxies. If you have without replacement, it already looks slightly more difficult because you have the finite population correction, you have extract that somehow, and the expression looks a little bit more difficult. And certainly what we somehow expect, if you have sophisticated sampling schemes, this equation looks much different and really not so straightforward. This was for the easy case where we can write it down. Good news, the next sampling design, we somehow also get different ideas. So coming back to our principles, the question is, does the EARN scheme deliver everything we are interested in? Well, here we're talking about multi-stage sampling, and the question is, how could this be expanded? I cannot make it so interactively today. I will try to do parts of it on my own. So we have the classical EARN, and now instead of having the different balls in the EARN, which you can draw the balls with the numbers, you have EARNs in the EARN. Draw that. And now in the different EARNs, you can find not necessarily the same number. I will try to make it slightly different, also to come to at least at some stage to an end. And now you see in a big EARN, we have small EARNs, and in the small EARNs, you have different balls. And the question is, how can we sample? So at least here, we can say we somehow have two stages. So we have the first stage, and we have the second stage. So the first stage is we draw EARNs, and then we draw the balls from the EARNs. And now certainly we have different opportunities. We can draw, case number one is we draw all EARNs and I don't know what to say, all balls. That's sensors. That's not really sampling. Some. What else do we have? We can do the opposite. We draw some urns, and then all balls from the selected urns. And then we have number 3, some and some. So the question is, why should we do that? Let's recap a little bit our harvest example. What is our harvest example, by the way, if we put it in this context? That certainly is this one here. So we take some square meters, throw that in the field, and then we take all straws which fall in this 1 square meter. That means some on the first stage and all on the second stage. And certainly we will call this then later cluster sampling. Yeah, because on the second stage the urns are entirely sampled like complete clusters. So if we then draw all urns and only some balls from each urn, why might that be interesting? Any ideas? Well, let's think about sampling in Europe. You want to have information from all countries, but you not necessarily need a census in the countries, and that means all countries but only some households in each country. Could also do that with federal states or whatever, and that's what we call then stratified random sampling. And finally, why should we also consider some? As I said, all doesn't make sense. It's a census, not really sampling. And that's the real 2-stage, call it somehow cluster sampling. That means that we draw, like if you are in a town, you draw some blocks of houses, but you don't interview all inhabitants of the blocks, only parts of it. But you would never draw all blocks, or you never would draw all inhabitants in the selected blocks. So that's a classical 2-stage cluster sampling. So big differences. So if you come back now, by what reasons do we do that? Well, I introduced it somehow only by practical reasons, like the harvest case, or that we have information in all federal states, or like practical reasons for the household sampling in towns, if we talk about blocks. All these concepts are more from practicability. They certainly have a huge variation in the costs, but also it might be interested in saying, but which are the efficient ones? And amazingly, we will find out, if you do it properly, that somehow stratified random sampling might also be either by practical reasons, I should write it properly, or by efficiency, because they can be constructed very efficiently, whereas in general, cluster sampling can immediately run into a disaster in terms of efficiency. Well, as a mathematician, I can also construct a case where cluster sampling is very efficient. Do you have an idea? Cluster sampling, how can that be very efficient? Well, imagine the case that all clusters have exactly the same distribution. Very unlikely to happen, but it could be. And if that happens, you can draw one cluster and you estimate with 0 variance, because if all are absolutely identical, they also have the same distribution as the universe, and then you have the very lucky case that cluster sampling is extremely efficient. With just one cluster, you sample with 0 variance. Well, just to be honest, you will never understand in practice whether you have this case. It would be a big surprise if this could happen. The practice is that cluster sampling in general has much higher variance than the others. Okay, I see that I'm slightly running behind the schedule. I'm lacking somehow in the interactivity, chasing me. But let's come to the first one, stratified random sampling. So what we do is, as we saw that before, we are somehow splitting the universe in disjoint groups. So all balls are in one of the small urns, but only in one of them. That's the mathematical notation here. And what you have done before is, if you go back, every of these urns is a classical urn. So we could easily say stratified random sampling is nothing else than somehow a mixture of simple random samples. The only question is, do we sample with or without replacement? And since we are drawing all, it's certainly without replacement on the first stage. In the second stage, we could draw either with or without replacement. In practice, we would very much prefer without replacement, but theoretically can do it with replacement. And that's why we do the same as before, just for each urn. The rest is putting together and do it in a weighted scheme. That's why all these formula is just a repetition from that what we had been doing before. The exception is that we have somehow the weights inside, and these weights rely on the proportion of the size from each urn to the universe. That's all, and that's how you could construct that. So the problem is, of course, that for each urn, you have to define a sample size. And the sample size is, of course, the major important thing here. And we call that sample allocation. Give a decomposition of the universe into L primary sampling units, the breakdown of the total sample size, small n, into L stratum specific sample sizes, N1 to NL, is called allocation. Don't forget, the total sample size is still fixed like in simple random sampling. But the problem is, how many would you sample in the first, the second, and third stratum, and so forth? And that's the so-called sample allocation problem. And here we have, of course, very, very different ideas. What ideas should come in? Practicability, costs, and efficiency. Don't forget that. I don't know anything more, only these three words, so they come back always. So before we talk about efficiency, we certainly have to talk about the variances, and in our case, certainly the mean estimator and stratified random sampling. You don't see any difference between simple random sampling with stratified random sampling with or without replacement, but for the variance, you certainly see that. You have, again, here the finite population correction term. The rest reads similar as before. Since the weights here are autonomous, then certainly, like if you have the mixture and the strata are independent from each other, you don't have any covariance terms, and that's why you write it just in the weighted form, but with a square of the weight as before. And you remember that, that's the variance of simple random sampling, now relying on every urn. So what kind of schemes do we, I forgot nearly that certainly confidence intervals read the same as before. Now you have here, of course, the mean and the variance of this stratified random sampling. And of course, what I did not say is, well, like in this, in this case, you have the variance of the estimator, which uses certainly values from the universe, which we don't have. In practice, you always, again, have to estimate that from the same sample. And what you do is taking the sampling variance, plug in the sampling variance, and then you get a variance estimator. I don't go into details yet too much about that, because that will be part on the next lecture, and then you will see some surprises once we tackle the real two-stage problems. But here it is more or less simply just plugging in, going straight forward, and then we have variance estimates either in the with replacement or in the without replacement thing. To get an unbiased estimator, there's a slight little correction, yeah? So this finite population correction has to be included. Be careful if you look in the literature, like if you compare Cochrane's or Law's book. In Law, in the meanwhile, you use cap as not as a random variable, but for the inferential variance in the universe. which already contains 1 over cap n minus 1. And then, of course, you don't need this term because then you don't have sigma squared, but the cap s squared, which already has the right inclusion inside. So we could see now an example in practice. Well, in general, the strata are given, the stratum sample sizes are given here as well, and then you have the means, possibly the standard deviations from each stratum, and then you can take an estimate, which is just nothing else than the weights of the averages, and then you get this estimate. So that's very straightforward. If you plug in the values, I don't want to do that because it's a waste of time. You can recap that at home. You get a variance estimate then because we have only S squares here of 0.14. And that already is really nice. You see, if you construct then a 95% confidence interval, the range of the confidence interval is already very narrow. That seems to be a nice result in our case. So that was the first example. But we could continue, of course. Now, if we change a little bit, the sample results remain now out of consideration. We assume known true stratum-specific variances that fly from heaven currently to make it easier, and we calculate the variances here. In the first case, using the allocation before, and now in the second case, we use this allocation. We have to compare that. Now it's 60, 180, 110, 150, and fortunately for A, yes, we see here now this is the sample sizes are in the denominator, and now we see also the sample sizes from before. And what we see is that the variances of the estimators vary from each other. So we see that the second allocation seems to be more efficient. And if we look what happened, so we have a raise of sample size, especially in this stratum, and somehow smaller sample sizes in others. And what is suspicious, if you look in details, this 150, so this stratum variance in stratum number 4 is very high. And if there's a little more vagueness in this stratum, it's likely that we need a little higher sample size to compensate the total variation. Yeah? The question is, how big should it be? That's not so easy to answer. Here it's obvious allocating a little more is nice. If you allocate too much, you get a turning point and it goes down. How can we construct that? Any idea? Well, we try to minimize the variance of the estimator with respect to the random variables, the sample sizes. So, and that's or the variable sample size. But before we do that, we think about some easy allocations. The first one would be we take equal allocation, which means taking the same sample size in each stratum, which is constant and just relies on the number of strata. Well, it's very easy to construct that. It may have disadvantages because it doesn't consider anything else but just the number of strata, and that's not so very fortunate. Let's go to the next one. The next one is the so-called proportional allocation. So now you allocate the sample size proportional to the size of the universe. That seems to be more intelligent. Is this the case? Well, it's not so easy to say. It depends on what you want to do. What we will later find out is if you do general accuracy comparisons, you cannot say anything about equal allocation. That's the big disadvantage. It can be good, it can be bad. You have no idea unless you have more information. With proportional allocation, you can at least say it's never worse than the simple Ernst scheme, so simple random sampling. So we at least get something which is as good as simple random sampling or better, and in many cases it is better. So that's the very nice thing. If we think a little bit further, of course, we get the idea like if you're interested also in the estimates of the subgroups, which is currently not the case. We're interested in estimates over the universe only. But if you're interested in estimates of subgroups, then it might be wise to avoid that some of the subgroups have almost no sample size. that you somehow try to get them upwards. So that might be an advantage from the equal allocation here. But that's a side argument which, to be fair, to be honest, doesn't count yet. What else could be done? Well, the optimal allocation. That certainly is already the solution. Now, you see here, you need certainly the standard deviations of all your strata. Well, again, where do we get that? That's the big issue. If we have that, it's nice. If we have proxies, it's very nice. But in practice, it's not so easy. Nevertheless, in many cases, like that what we were constructing for the German census with very good proxies, a very highly correlated variable, and then it works certainly pretty fine. And what we expect, of course, if we do an accuracy comparison, this should be always the best, under the assumptions we know the sigma q. By the way, to construct that, take the Lagrangian, minimize the variance subject to the given sample size, and then you get directly this formula. The big difficulty is here, it could happen like if you have something like income as a variable and you have income classes, it's very likely that the highest class has a huge variation, but the class is somehow small. And then it might happen that you get an optimal allocation where small nq is larger than cap nq, which certainly is rubbish. Oh, now I used the word I tried to avoid earlier. Be careful. That's the so-called overallocation. By the way, that can also happen in equal allocation. If you have extremely unbalanced in terms of size strata, then you have to be very careful for that. So, but that's a big disadvantage of the optimal allocation, and you have to be careful. Also, what can happen here is that some of the strata, if you have almost very small variation of the values in the stratum, the optimal allocation would compensate that, okay, then we don't sample here, or we have almost no sample size. That's why in practice you always would say, well, we don't want to have more than 100% sample size. We definitely do want to have 0 sample size. You would somehow fix a minimum sample size for each stratum and probably also a maximum sample size. So we have constraints. Before we come to the constraints, well, we certainly have here an example. If we construct then the Niemann-Chuprov allocation, then we can see what we get. Be careful, again, we certainly have here the case that sample sizes are always integer numbers. If you have the optimal allocation, you get rounded values, of course, only, and you have to be somehow careful with the rounding. And finally, the best result in our case, for example, is then taking the optimal allocation. This variance is certainly smaller than the variance in our example 2-3 by definition, since we know the true variances in each stratum. Well, without replacement sampling would have a small correction term. This can again be avoided taking the classical cap S like in Law's book, then you don't see that. And I said, well, you have to be careful that you can have the overallocation and you have the integer optimization approach. That has to be considered, but we have a generalized approach pretty soon. Another thing could be to integrate costs, the so-called cost optimal allocation. It's similar to the optimal allocation, but now you have a linear cost function with stratum-specific but constant costs for drawing each element in a certain stratum. You have to be very careful. Certainly it's the case. The more expensive drawing an element in stratum Q is, the less elements you would sample. You try to avoid costs, but that certainly means it's a loss in efficiency. Once you have in high variation strata, high costs would be a disaster, but it can happen. Problematic is in practice you have to consider the costs. Indeed, it would be very interesting taking like interview lengths or something like that. Then you would work with OpenStreetMap. We have currently we are very close to running a master thesis on that. But then you don't have fixed costs in each stratum, and you have to consider variable costs. And then the optimization problem, of course, is a little bit more sophisticated, I would say. So again, we have an example, but I think we should not tackle that. I would love to somehow get at least this second part. And again, we have the same problem. Cost optimal allocation also has the problem of over allocation and certainly the integer problem as the others as well. I said under certain circumstances we can compare the variances, and I just give the results. I think the formula is straightforward if you plug them in. What you can always say is you have simple random sampling. The variance is at least as high as the variance for proportional, taking stratified random sampling with a proportional allocation. In most cases, you can construct at least a better allocation or better, slower variances. And certainly what we also know is that the optimal allocation by definition, again, must be better. There are cases where there is no differences, and the question now again would be, when do we have a gain of efficiency and when not? So if we look at the first equation, we see here the two terms already here. The difference in variance is 1 over n sigma b squared. Sigma b squared is the variance between, that means the variation of the means. So if you have something like income classes, you have a huge variation of the means because they're somehow separated. If you have overlapping strata, the means are close to each other. Then this term would be almost 0. So the higher the variation of the means is, the higher is the gain of efficiency going from classical simple random sampling to proportional allocation. And if you look then at the second term, you see here the difference between proportional and optimal allocation is set by this term here. What is this term? Well, it's a somehow weighted variance term, but the variance of the sigmas. And the variance of the sigmas means the higher the variation of the standard deviations between the different strata is, the more heterogeneity you have, and then you should look for the strata with high variances and allocate more. That means if the stratum variances are varying a lot, then it might make sense to go to the optimal allocation. You would get another gain. If you already know that the variations are not so much, it probably doesn't make sense. But if you have something like income class, it's always likely that the highest class has a much higher variation than the lower classes. That's where surely the optimal allocation should be better. So, and here everything is somehow put together. And another thing I said...
Could I interrupt you a minute, because it's getting to 18 hours and I see that you have 92 slides, so is that second for your next webinar, or do we need to go rush through in a couple of minutes?
At least 2 minutes, please. I'm nearly at the end of this part and...
Yeah. Okay, very good, very good.
Okay.
Go ahead.
So, and as I said, the optimal allocation and the others as well have the difficulty that you're not considering over-allocation or minimum constraints. And that's why we constructed somehow an optimizing process for optimal allocations, an expanded version where you can include lower and upper sampling fractions in each stratum, and certainly also a number of maximum sampling units. Like if you draw then clusters that could be included and say, okay, but with the clusters you don't know the number of inhabitants, that can also be another constraint. And this formula means nothing else. Well, if you have only one area of interest, then it's straightforward, the classical optimal allocation, but you can treat it as well as small area problems, saying, okay, you want to have an optimal allocation for each of the regions, and you compensate that by a classical 2 norm. And this is the so-called box constraint optimal allocation. And we invested that for the German census, and that helps with all the classical problems. You never get over-allocation or nearly empty units. The problem is the optimization algorithm is not so straightforward, but we're very close to launch our package for that. The exact solution is in this paper, then some numerical investigations with this specialized algorithm is in this paper, and what is essentially interested, recently we have also published a purely integer version which I thought is very difficult once you have 20,000 strata. In the German census, we had more than 20,000 strata, but be sure we have a full optimal allocation with integer values with an awful lot of constraints, and this integer solution was found in 0.1 seconds, even in this large size problem. And now it makes sure that we really have the integer solution and we don't have problems with a lot of roundings, which may become difficult. So Haley reminded me that I was too slow today. I will rearrange a little bit next week, but many of the things are much faster for the last parts of this. I will skip that to the next lecture, and I will already upload the slides that you have the advantage of looking inside. Thank you very much for attending this lecture.
Okay, thank you. Thank you very much, Ralf, for this very enthusiastic talk, of which I understood very little, but I'm pretty sure that the audience with us were following you step by step. The recording of this webinar, I think, from our WebEx colleagues will come tomorrow, and I will also upload this presentation on the EMOS website and send you the links tomorrow. The next webinar will be in 2 weeks' time on the 17th of May, and that will be our Slovenian colleague Mojca Bavdac talking about visualization, and I think Ralf comes back sometime in June. Date I now don't remember, but the program is there on the internet. I would thank everyone who were with us today, who went through the troubles of new ways of connecting with audios and phones and helping us to learn what works and what doesn't with the WebEx tool, and we will take our lessons home and try to improve for the next time in 2 weeks. For that, thank you very much, and bye-bye, and we hope to see you back. Thank you.
Bye-bye.